The motion of a rectangular loop in a magnetic field. The magnetic field is acting into this one and it is fixed in this region only, and a rectangular loop of length L and this width, it is not mentioned here, is moved through this uniform magnetic field here with a velocity v towards right. You can say in this, as the coil rectangular loop is moving towards the right side, slowly the number of magnetic fields acting or passing through this loop will decrease. That means flux is decreasing here. First point, when it is pulled towards right, flux through coil decreases. Second one, as the flux decreases, that means there is some change in magnetic flux linked with the coil, which is going to be minus d phi by dt. As the flux is decreasing, so EMF will be generated here, and this can be given as E is equal to minus d phi by dt, which is equal to minus d by dt of flux is equal to B into A. So what is the EMF induced in this coil? Minus d by dt of B into, what is the area of this coil? The area is given by, this is the area through which flux is passing here. We need to consider only this area which is inside the magnetic field. Length L, let us say this distance along x-axis, let me take it as a x here. So what is the area through which the flux is passing here? I am going to write in place of A, this will become L into x. So EMF induced is given by dB, d here. Magnetic field is constant, length of this one is constant, this length is constant, but x is changing with time. Here x is this much, when it is pulled outside, when it comes to this position, x will decrease. So x is varying here, so I can write minus dx by dt. So EMF induced in this one is equal to BL. As x is decreasing, no problem. If x is increasing, we call it as a velocity, increase in velocity. Here decrease here, minus indicates that x is decreasing with time. So this is nothing but the velocity with which the loop is pulled out. So this EMF is given by E is equal to believe. Now what is the induced current here? E by, let us say resistance of that coil is R, which is given by BLV by R. Whenever the flux is decreasing here, the direction of the induced current is such that it will try to increase the flux in this one. Here the flux through the coil is decreasing when the loop is moving away. When the loop is taken out, the flux through the loop is decreasing. So the induced current is such that according to Lenz's law, it will try to increase the flux. To increase the flux, that flux also due to induced current must be inverse. So as it is inverse, the current should be clockwise direction. So what is the direction of current here? This I must be clockwise. So as the current passes through this one in the clockwise direction here, this is the direction of flow of current in this one. So from this one we can write, as it is a clockwise direction, now I am going to write what are the forces experienced by this four sides of the loop. Remember students, the side which is out of the magnetic field will not experience any magnetic force. Why? Because the magnetic force experienced is given by BIL. So now I am going to take this as 1, 2, 3, 4. These are the four corners. First corner, second corner, third corner, fourth corner. So what is F12? This is 0. Why? Because there is no magnetic field here in this region. Field is up to this boundary only. Beyond this boundary there is no magnetic field. So force experienced by this one will be 0. What is F23? F23, here you can write field is into the board. Now current is passing like this towards this one, so force will act downwards. So F23 is acting downwards, which is going by B, current I, length of the coil or the rod or that wire within the loop is X only. So I am going to take it as BIX. Similarly F34, this is downwards. Now here field is inwards, current is flowing upwards, force is outside. So this is the direction of force 34. F34 is given by B, current I, length of the conductor here is given as L. Now F41 is given by B, I, length of the conductor within the field is X once again, x. But what is this direction? So field is inside, current is flowing, this force will be upwards. So this is the upward force, F41. Here F41 is acting upwards, F23 is acting downwards, both are equal and opposite. So what is the total flux here? These two get cancelled here because these two are equal in magnitude but opposite in direction but acting along same line, that's why they cancel with each other. So the net force experienced by this conductor is given by 0 plus BIL, which is equal to BIL. Now how much force is required? Here this much force is acting in this direction. To move this loop through this magnetic field, I need to apply a force which is exactly equal and opposite to this one. If I apply a force less than this value, I cannot move this loop through the magnetic field. If I apply a force exactly equal to this force, then I can move this one with constant velocity. Why? Because this is the force which is acting towards left in this direction. I need to apply a force which is acting towards right. So the force which is acting towards right is given by F is equal to BIL. So according to this, the force experienced by this entire loop is given by this much, and the force given by us to move this loop with a constant velocity, when these two forces are equal and opposite, net force will become 0. Net force is 0 means body moves with constant velocity. So force required to pull loop in the magnetic field with the constant velocity is given by constant velocity or speed is given by equal to this, which is equal to BIL. So now I am going to write how much force is required. Force required is equal to BIL. So B into I is equal to BIL by L. So the force required to pull this loop through the magnetic field is given by B square L square V by R. This much force is required. This is the force required to pull this one. So after that, how much power is required to pull this one? They may ask you to find out the power. Power is nothing but force into velocity, work done by time. So you can write a force into velocity, which is given by B square L square V by R into V, which is equal to B square L square V square by R. This is the power required to pull this one. It is also found that the power produced in this loop due to this pulling through a magnetic field is also equal to B square L square V square by R only. A problem, a bar of mass small m, this is a bar here, this is the bar that is given. Its mass is m and length L, moves on two frictionless parallel rails in the presence of a uniform magnetic field directed into the plane of the paper. So this is magnetic field B here. The bar is given an initial velocity of Vi. So what is the initial velocity that is given to this bar towards the right side? So it is given as Vi here to the right and released. Find the velocity of the bar, induced EMF across the bar and the current in the circuit as function of time. Here it is not pulled continuously, it is just moved with some initial velocity Vi, after that it is released. So whether it moves, whether it stops, whether it comes back, we will check it and we will find the final velocity of the bar as a function of time. First of all, in this problem, whenever a conductor is moving in a magnetic field, so this area slightly increases, gradually increasing. As the bar moves from here to here, the area through which the flux is passing will increase here. So according to that Fleming's right hand rule here, this is the field direction. Forefinger will give the field direction, and this is the direction of motion of the conductor. So this will be the direction of flow of current in it. So the induced current will pass through this conductor in the upward direction. So this is I. Now according to Fleming's left hand rule, according to Fleming's right hand rule, current will be upwards. So as soon as the current passes through this wire, as it is open circuit, current will not pass through the other side. Current will come in this direction. Current passes through this one, whose resistance is R here, and it passes through this one. So current will continue and current moves in anti-clockwise direction. So solution, due to motion of bar in magnetic field, current flows, current is induced in the bar and moves in anti-clockwise direction. Moves or flows in anti-clockwise direction or counter-clockwise direction. So after this, now I found the direction of current by using the Fleming's right hand rule. When the current is flowing like this through this conductor, now let me apply Fleming's left hand rule here. Field is inwards, current is flowing upwards, a force will act in this direction. So the force will be experienced by this conductor in the opposite direction. So from this what we can say, the initial velocity of the bar is towards the right side, the force or magnetic force acting in the bar is towards left side, opposite to the direction of motion of this conductor. So this is not the actual force acting on this one, or it is not the accelerating force here, this is a retarding force as it is opposite to the direction of motion of the conductor. So what is the retarding force? The retarding force is nothing but the magnetic force. Retarding force, which is equal to magnetic force, is given by BIL. According to the formula, F is equal to Bill sin theta. Here I can write minus here. Why? Because here the velocity of the bar is towards right side, the force is acting towards left side. That's why I am keeping minus here. This must be equal to the acceleration produced in the bar A into mass of the bar M. And it is clear that from the equation the acceleration is negative. So A is equal to minus Bill by M. So I am going to write this as acceleration is equal to minus Bill by M. But what is the current induced in this coil? We know that the current will induce the coil I is equal to E by R, which is equal to Bill U by R, where induced EMF is given by magnetic field B, length of the conductor L, and velocity I. So Bill U by R. So here I am going to replace this one as B by M, and the current flowing through this conductor is Bill U, B L V by R into L. So this is the equation to find out the acceleration of this conductor. So acceleration is given by, here minus is common, B square L square V, this is B into B square L into L by MR. But students, here you can see the force acting on a conductor depends upon the current flowing through this one. The current once again depends upon the magnetic field here, and the current also depends upon the acceleration. Here, as the force is acting in the opposite direction, the velocity is not uniform. So velocity is changing. Current depends on velocity as well as the magnetic field. As the velocity changes, current changes. As the current changes, acceleration also changes. So these are all linked with each other. That's why acceleration is not constant. So here I am going to write this acceleration as dv by dt, the rate of change of velocity is known as acceleration, minus of b square L square V by mr. So this can also be written as I am going to bring this V this side, I can write this as dv by V is equal minus b square L square by mr dt. Now I am going to integrate this one with the limits are here. Here the variable is time. So at 0 seconds, the initial velocity is given as Vi. So I am going to write here Vi. And when time t, the velocity is V. This is integral dv by V. We can write it as log V. So or ln V. So natural log V here with the limits Vi to V. Vi to V, which is given by here magnetic field is constant, length of conductor constant, mass of conductor constant, resistance is constant. These are all constants. So first you write them outside, minus b square L square by mr into the time integral dt will be t. If you substitute t minus 0, you will get t only. Now you can write this as log V with limits, you can write ln V by Vi after substituting this one, log V minus log V, I can write as log V by Vi is equal to minus b square L square by mr into t. Now, if you take antilog on both sides, you can write V by Vi is equal to e power minus b square L square by mr into t. or V is equal to, finally I am going to write here, what is the velocity at a function of, as a function of time. Here from that equation you can write velocity is equal to initial velocity into, so velocity is equal to the initial velocity into e power minus b square L square by mr into t. So the velocity v is given by the initial velocity into e power. Let us say this is a constant, you can represent this with any value, either with capital T, small t, or whatever may be. Generally it is a time only, because the dimensional formula for this one will become time. That's why I am writing minus t by 1 by t. So this is 1 by time. So or you can represent this minus t by x, minus t by y, minus t by any constant here, but where this is the velocity as a function of time. But remember students, as it is negative here, velocity decreases exponentially. Why? Because as it is negative sign here, if it is positive sign, velocity increases exponentially. Here what I can write, conclusion, velocity of the rod decreases exponentially with time. So after that they are asking us, after finding the velocity, now I need to find out what is the induced EMF and what is the current in the circuit. Induced EMF is given by EMF is equal to, we know the general formula, believe. Here B constant, magnetic field into the board is constant, L length constant. So what is the velocity? Just now I got this equation. So it is a function of time. I am finding EMF as a function of time here. So I can write this as VI e power minus t by tau. This is the equation EMF. Similarly, they are asking us to find out the current in the circuit. What is the current? I know that I is equal to V by R or E by R here. Induced current is equal to induced EMF by resistance in the coil. This resistance is equal to R here. So I can write B L V I e power minus t by 3 by R. This is the induced current in this one. Self-induction. The property of a coil that opposes the growth or decay of current in it is called self-induction. So now let me take one coil here. This is a coil which is connected to a battery with the help of a key here. Now in this coil here, this key is open here. This is key, this is battery, and this is the coil. In this, what happens in this coil when the key is closed? First, when the key is closed, what happens? Now let me close the key here. So I am closing this key here. So if we close this key, then the current through this coil gradually increases. Now let us say in the 0 seconds, this is the time, and let us say this is the current. At 0 seconds, the current is 0 amperes. The maximum current that can be given by this battery to this coil, let us say 5 amperes. So this will become 5 amperes. So how much time it will take for this current to grow up to 5 amperes? It will not be 1 hour or 2 hours. It may be less than 1 second. So let us say this is 0.05 seconds. So at 0.04 seconds the current will be 4 amperes. 0.03 seconds this will be 3 amperes. 0.02 seconds will be 2 amperes. 0.01 seconds it is 1 ampere. So at 0 seconds it is like this. Now when the current increases, it will take some time for the current to grow. But it is found that when the maximum current is passing through this one, so after that the constant current, as it is a DC source battery, a constant current flows through this coil. But if it is a resistor, small resistor like this, so these are the values for this one, for this circuit, or these are the values. But it is found that when the time increases, current is not increasing that much easily. Current is also increasing, but not similar to this pattern. Why? Because these coils will oppose the growth of current. It will not allow the current to grow that much easily. So the property exhibited by these coils to oppose the growth of current is called self-induction. Opposes growth or decay. When the current is decaying also, the coils will not allow the current to decay. So opposes growth or decay of current in a coil. So in this case, what I am going to write, when the current is increasing from 0 to 5 amperes here, now let us say first 1 ampere current is flowing here. When the current is 1 ampere, so as the current is flowing through this one, a magnetic field will be developed through this coil. So this is the direction of the magnetic field here. So this is the direction of magnetic field. Now if the current increases to 2 amperes, then the magnetic field through the coil also increases. When the current is 3 amperes, 4 amperes, 5 amperes, like this, whenever this current increases, then slowly the magnetic field through the coil also increases. So from this what I can say, the flux that is passing through this one directly proportional to the current passing through this one. If the current is maximum, then flux will become maximum. After that, as it is a DC battery, when it reaches the maximum current, then flux through the coil will become maximum. And after that, there will not be any change in the flux. So EMF will not be induced. If current is constant in the coil, flux will be constant, because as both are directly proportional to each other, as the flux is constant, the rate of change of flux will become 0. So then EMF induced in this one becomes 0. So this is the case when the current through the coil is constant. But you can see in the starting stage, the current is gradually increasing here. Whenever current increases, we can say that the I is changing. Whenever I changes, due to this flux through the coil changes. Why? Because B increases, B magnetic field through that coil changes, and this flux through the coil changes. As a result, d phi by dt is not equal to 0, as E is equal to d phi by dt or minus d phi by dt. So this is a non-zero value. That means EMF will be induced in the coil. So these are the different points that you have to remember here. This change may be increase in current or decrease in current. First let me explain about increase in current, that we call it as growth of current in the coil. When the current is increasing, now here as you know that phi relative to I, when the current is increasing, the field through the coil also increases. Here this is just similar to a solenoid. Magnetic field is going to be mu naught Ni. So whenever current increases, magnetic field induction through the coil will increase. We know that flux phi is equal to B into A. Here first when I changes, B changes. When B changes, the flux changes. When flux changes, EMF will be induced here. When EMF is induces, according to Lenz's law, this EMF is always opposite to the EMF of the cell or battery that we are connecting here. So this is called induced EMF. This induced EMF is due to the flow of current through this coil. Induced EMF depends on rate of change of flux. So flux depends on magnetic field induction. Magnetic field induction depends on current. So these are all linked values. So this EMF is directly connected to this current. Whenever there is a change in current, EMF will be induced in the same coil. So this is called a self-induction, the process in which EMF will induce in a coil which opposes the growth of this current. This EMF will oppose this current according to Lenz's law. So current induced in the coil produce magnetic flux which opposes the main flux. Main flux is a flux due to the current flowing through this coil is main flux. So due to this one, the induced flux will always oppose this main flux. That means when the key is closed, when the current is increasing from 0 to 5 amperes, when the current is increasing, number of lines are increasing, flux increases, field induction increases, as it is increasing, whenever there is change in magnetic flux, an EMF will be induced here. So what is the total EMF when the current is increasing here? The net EMF is given by capital E minus small e. Why? Because this is called back EMF. Why? Because this is the EMF which is opposing the growth of current, and this is the EMF which is giving the current here, but this EMF is opposing the growth of current. It will not it will not allow this current to grow. That's why this is called back EMF. Self-induction will delay the growth of current in the coil. So when the current is trying to grow, this self-induction of this coil, the property of this coil will not allow the current to grow as it required. Now here what we can say, the total flux will increase with the coil, that is N phi, where N is the total number of turns in that coil, flux is phi is the flux will increase with one coil, directly proportional to I. So N phi is equal to Li. This is the relation between flux and current here. So this is equation 1. If we differentiate this one, here we will get by differentiation N into minus d phi by dt is equal L into di by dt. So if you multiply with minus on both sides, you will get this is nothing but EMF induced here, which is given by E is equal to minus L di by dt. Here actually minus is not there. If you differentiate the N here, N as it is N, phi with respect to time, d phi by dt is equal to L di by dt. But N d phi by dt is not EMF. EMF is equal to minus N d phi by dt. So N d phi by dt is nothing but minus E. That's why in place of N d phi by dt I am writing minus E is equal to L d phi by dt. So EMF induced in this coil due to the rate of change of current in the coil is called self-induction. Now what is this L? This L is called coefficient of induction or coefficient of self-inductance or simply self-inductance. So the process is self-induction and this is called self-inductance. So what is this L? L is given by E by di by dt. So what is self-inductance? L is defined as self-inductance. So this is the amount of EMF induced in a coil when the rate of change of current is exactly equal to 1 ampere per second. So if di by dt is equal to 1 ampere per second, then EMF induced is called self-inductance of the coil. Let us say when the current through this one is changing at 1 ampere per second, for every second let us say 1 ampere current is changing, increasing or decreasing. That's why I am telling changing. So if 1 ampere current is changing for each second, let us say 0.2 volts is induced in this one, then the self-inductance of this coil is known as 0.2. But what is the unit of this one? So from this we can write, from this equation, self-inductance is measured, L is equal to E by di by dt. So this is volt by ampere per second. So self-inductance is measured in volt by ampere per second. So this is also called Henry. So what is 1 Henry? The self-inductance of coil is said to be 1 Henry. If 1 ampere current is passing through the coil changing at the rate of 1 ampere per second and producing 1 volt EMF in that coil, then the self-inductance of the coil is said to be 1 Henry. Very, very important definition for UC, but in competitive exams also they may give 1 Henry equal to dash. So 1 Henry is equal to 1 volt by 1 ampere by second or volt second by ampere. So remember this one, 1 Henry is equal to 1 volt second by 1 ampere. This is the relation between this SI unit and the units which we are using for electrical physical quantities.